Okay, so here we take a look at how to derive the expression like this, k times 2p over c cubed. Okay, so here we have two charges. So if we would like to calculate the E field on this z-axis, then we would like to calculate the E field generated by these two charges individually, and then we just add them together. And hopefully, if it is on this z-axis, these two E field will point to the opposite direction. So which means that the vector sum is just subtraction. It's just a subtraction on the z-axis. So it is easy to derive. Otherwise, if you find any point, just say this point, then the E field will be somewhere like pointing to, will be something like I'm not sure, something like this. Okay, something like this. The electric field line would be something like this. But yeah, this is we can't find an elegant expression of the E field. So here we just focus on the E field on the z-axis. Okay, so here E will be E plus minus E minus. Okay, E plus is the E field generated by the positive charge, and the E minus is the E field generated by the negative charge. Okay, so here E plus will be K times Q. Okay, we have a plus Q here, negative Q here. So K times plus Q over R plus quantity square. R plus, what is R plus? R plus is actually here. Okay, counting from this positive charge to the point Z here. Okay, Z is actually starting from this middle point. Okay, so here we have R plus, and similarly here we have E minus. Actually it's like K times negative Q, K times negative Q. So we just put this negative side inside. Okay, so this is actually the magnitude of the E minus generated by negative Q. Okay, so here we have a negative KQ over R minus square. Okay, R minus is starting from this negative Q up to this point P. Okay, so nothing special here. Okay, so here we try to factor out KQ. Factor out KQ. So here we have a KQ outside, and then we have the expression R plus R minus in terms of some known variable like Z and D. Yeah, Z and D would be the known variable. Yeah, so actually we can see that R plus is actually Z minus D over 2. Okay, so you can see, yeah, this part is D over 2, so R plus is actually Z minus D over 2, okay. And similarly, R minus is actually this Z plus D over 2, okay. So here we have C plus D over 2 here. And yeah, so here we also try to factor out this Z, factor out this Z. So here we will have C squared, because yeah, this Z is inside this square. This Z is inside this square. So when we try to factor out this Z, we will have C squared outside, and we will try to divide this thing by Z, divide this thing by Z, and then we will factor out C squared outside. Okay, so it doesn't change anything. Okay, so in this case we have a 1 minus D over 2Z, and this term is similar, 1 plus D over 2Z. Okay, something like this. Okay, so here we try to just add them together, or just do this subtraction. So in such a way, the denominator will be this term multiplied by this term. Okay, so this This is the denominator. And for the numerator will be this term minus this term. Okay, so here a plus b squared will be a squared plus 2ab plus b squared. And then this is a squared minus 2ab plus b squared. So after the subtraction, it only has the 4ab. 4ab means 4 times 1 times, this term will be 4 times 1 times d over 2z. Okay, so 4 and 2 partly cancel. We have a 2d over z in the numerator. Okay, so finally we make use of this far field condition. Okay, this is the far field condition that we assume, because if we don't have this far field condition, the expression will look like this, not that elegant. So here, if we try to assume that z is much larger than d, then we can assume that this is close to 0. This is close to 0. This is also close to 0. Okay, so the denominator will be just 1. Will be nothing but 1. Okay, so it makes things much more easy. Okay, so in that case, if we assume that z is much larger than d, so the final answer will be k times, here we have 2qd, and then this z merged with this c cube will be c square will be c cube here. Okay, so finally we have k2qd over c cube. And if you still remember, qd is actually the electric dipole moment or dipole moment. Actually, this electric dipole moment or dipole moment here. So P equals dq. So finally, it becomes k times 2p over c cube, okay, which is the E field generated by a dipole along this z-axis. Okay, Okay, so far any questions? No. Okay, so here we will start to have something more difficult here, because we will try to make use of the calculus to calculate the E field generated by some special structure. Okay, so here is the first one, is the electric field due to a line of charge. 这是一个线的电荷。 Okay, so and more specifically, this is actually a charge ring. Okay, 这是一个有电荷的环。Okay, so the equation for the E field set up by a particle does not apply to an extended object with charge, which means it has a continuous charge distribution. Okay, so previously when we only have a single charge, then we can apply the E equals k times q over r squared. Okay, if there's only one single charge, we can just make use of this equation for a single charge. If we have multiple charge, let's say 2 charges, 3 charges, or let's say 100 charges, then we can just make use of this equation. Of course, there may be a vector sign, and then we find many E1, E2, E3 up to E100, and then we add all these vectors together. But here, the idea is if we have a continuous charge distribution, we cannot really count how many charge there is. So we actually need to make use of the calculus so that we may be able to calculate the total E field. Okay. So here it says to find the electric field of an extended object at a point, we first consider the E field set up by a charge element. Okay, charge element dq in the object, where the element is small enough for us to apply the equation for a particle. Okay, then we sum via integration. Okay, components of the electric field dE from all the charge elements. OK， 这个就是这个积分的那个积，就是那个定义嘛，就是那个 Riemann sum 的定义嘛，就是现在我们有一个环，它是连续的 ，it has a continuous charge distribution. Okay, we may not be able to count how many charge there is, so we need to separate into many small pieces. Okay, let's say ds, one ds, and another one. We cut it into many small pieces. Of course, yeah, in this figure it's not small enough, but yeah, it's just for you to have a visualized way to see. Okay, everyone is you assume it is small enough to consider, or this one has a constant distance from this charge element to the point we concern. Okay, and then we can apply this equation for this small element. Okay, so we can find dE for this small element, and dE for next one, so on and so forth. Of course, if there is a continuous charge distribution, when we try to separate into many infinite small elements, there will be infinitely large number of dE. Okay, so we add all this dE together, it will be an integral, an integration. Okay, 就是你有一个连续电荷分布了，那你就把它切成一小块一小块，每一块我们就可以用原来的那个 E 等于 kg over r square， 因为你切得很小之后，那一小块里面它就等于说它有一个电荷，然后跟我们关心的点是一个固定的距离了。但这个例子是特别的，这个例子其实不需要用积分了，但是就是告诉你说可以用这种方法。原则上这个题目的话其实不需要，因为它其实这个圆环跟它轴上面的某一个点到这个圆环的任何一个部分都是等距离的，因为这是一个圆嘛，这是一个圆，所以它圆性到这个圆的距离是固定的嘛。那在这个轴上面的任何一个点到这个圆环任何一个点的话，也是固定的距离的。所以这个题目其实不需要，但是其实是让你理解这个方法如何操作。那你开始理解这个方法怎么操作之后，就可以用在一些一定要积分才能算的题目上面。OK。So a ring of a uniform positive charge, a differential element of charge occupies a length ds, greatly exaggerate for clarity， 就是夸张的大的，其实它应该是非常小，但是我画的非常小，你就看不到嘛，所以就是它故意画的比较大一些。Okay, so this element set up an electric field dE at point P. Okay, so the first step is to just separate into many small charge elements, and then the second step is to cancel some of the components. Okay, some of the components. So for this one, we can actually cancel one of the components. Okay, so let's see. So for example, here we have ds here, and then the E field we concern at point P. Okay, so here, suppose this ring has a positive charge Q. Okay, so ds here. So when we try to connect this small element with this point P, okay, so we know that this is positive charge, so dE points to somehow like the bottom right, top right. Okay, so here, of course, if we only have this dE, we cannot cancel anything, but hopefully, as much as this is a ring, this is a perfect circle, so we can always find the symmetrical part somewhere here. Okay, so you can consider this is also another ds. Of course, this is not not really the same, but yeah, you can consider. We can always find the symmetrical part. So in that case, this ds will generate a de somehow pointing to this side. Okay, and then of course originally a 3D graph will look like this, and then here we try to consider the cross section figure. Okay, so to look like this. Okay, so this one is actually this one, and this one is actually this one. So as much as these two is symmetrical with respect to the center point of the ring, so in that case, when we try to decomposite this dE on this axis and the z-axis, and also decomposite this one into this axis and z-axis, we can actually find that these two should be the same, because we will assume that the charge is uniform distributed， 是均匀分布的，而且它们跟这一点的距离是相等的。Okay, so these two will perfectly cancel, which means only the z-axis component will remains after this kind of cancellation. So yeah, so that's the idea. So the components perpendicular to the z-axis cancel. The parallel component adds. Okay, so actually, finally, we only need to consider this component and do the integration for this z-axis component only. And actually, we simply assume that the angle here is theta. So actually, also this angle is also theta. So you can see the dE will have an angle with theta, with the z-axis. So in this case, this is dE, the magnitude is dE, so the z-axis component will be dE times cosine of theta, dE cosine of theta. Okay, so here is the last part is to add the components using the integration or integral. Yeah, so here, just now we know that the z-axis component will look like this, dE times cosine of theta. And actually, cosine of theta, you can actually find the value of cosine of theta, which is z over small r. Okay, z over small r is a cosine of theta. Okay, so in this case, actually, we will consider z is a known variable and r is a dependent variable. So we'll try to express this r using small z and capital R. We will also consider this r will be a known value, and then we will have the z as a variable to make things easier. Okay, so yeah, so actually we would like to use the Pythagorean theorem to express r as square root of z squared plus capital R squared. Okay, something like this. Or this square root, we can just write it as to the half order. Okay. Okay, so this is the expression of cosine theta looking like this. Okay, so here we will try to plug this thing back to here. Okay, and also dE for dE is actually this part. dE is actually this part. So here for dE we will have this term is k, and then dE should be something like k times dq over r squared. Okay, r squared. So actually r similarly is actually this one. So r squared will be c squared plus r squared. Okay, so here we have k times z squared plus capital R squared. And then for the dq, we will try to change the variable as this lambda ds. Lambda ds. Okay, so actually ds is the length. Ds is the length. And what is lambda? Lambda is actually the linear charge density. Linear charge density. We assume the charge is uniform distributed and the total charge is Q, although lambda is just a temporary variable. We will not have this lambda at the final solution, but at this moment we still need this because we would like to do the integration, but integration of dq is not trivial to work with, so we would like to change the variable as lambda is the linear charge density times the ds. OK， 就是长度，就是每个单位长度的电荷量乘以长度，这是一个长度嘛，所以就是这个 dq 就是这个东西。Okay, so the SI unit for the lambda will be C over meter. Okay, so this is the SI unit for the length. This is the SI unit for the charge. So C over M will be the SI unit for the lambda, the linear charge density. Okay, so actually this is dE. So we plug this one here. And then also cosine of theta is this one. So we put this term here. Okay, so actually R squared is actually this one. So we can actually merge this term together as C squared plus capital R squared to the 3 over 2 power. 3 over 2 power. Okay, so and the remaining stuff we have this one is K, and then we have a lambda ds times Z. So we have a Z lambda ds, okay, arranging like this. So we actually like to integrate this dE cosine of theta, and then with the expression like this. Okay, so finally we can do the integration, okay, to find the final E field generated by the whole ring. Okay, so actually E equals integration of this line. So we have a dE cosine of theta, and then plug in the expression here. So here we have a 1 over 4 pi epsilon naught at Z lambda over this term ds. Okay, so actually we would like to integrate ds for the whole ring. Okay, so according to your primary mathematics, you know the circumference of a circle will be 2 pi r. Will be 2 pi r. So we actually integrating ds from 0 to 2 pi capital R. And actually, for the whole expression here is a constant to s. Okay, so that's why I just mentioned that this example, we don't actually need the integration, but just let you know how every step works at this simple example, and then we can just apply this method to other cases. Okay, so hopefully this is a constant, so which means that this integration will be really easy. So it's just like doing an integration similar to integration of 4 dx times from 0 over 3. Okay, so this is easy. So it is just nothing but 3 times 4, which is 12, something like this. Okay, so similar for this case, the integration for the constant will be like this constant, we just put it here, and then this 2 pi r minus 0 is 2 pi r, so we just put this 2 pi r here. So nothing special. Okay, so finally we can do some simplification. So just now we assume that the linear charge density will be lambda. So we should have lambda equals the total charge Q over the circumference of a circle, 2 pi capital R. So we should have this expression. Okay, so finally we can just collect this 2 pi capital R times lambda, 2 pi capital R times lambda as Q. So we change these 4 terms to be Q. So finally we get this expression. Okay, so finally we have E equals, this is K times QZ over Z squared plus capital R squared, whole thing to the 3 over 2 power. Okay, so this is the expression of this ring. Okay, so if we don't assume Z to be much larger than R, then it will be the final solution. But similarly, if we also assume this far field condition, which means Z is much larger than capital R, then we can also do some simplification, which means in this term, if Z is much larger than capital R, then we can simply ignore this one. So we have a C squared to the 3/2 power, which becomes Z cube. Okay, so it becomes Z cube. So this Z cube will be partly cancelled with this Z, so it becomes C squared here. Okay, so this is quite an elegant expression. And the idea here is like, if you consider a point P which is very, very far away, it is just equivalent to something like if we have a point P here. Okay, so if all the charge is concentrated at the center, so this is Z. Okay, so the E field generated by point charge Q at this point P will be this expression. Okay, so if it is far away enough, this ring is look like a point charge. All charges concentrate at the center. Something similar to the shell theorem in the last chapter. Okay, so far any questions? No. Okay, so here let's take a look at a sample problem. So here, for this sample problem, we really need the integration. So okay, so here we can see that it says plastic rod have a uniform distributed charge -2. The rod has been bent in a 120 degrees circular arc of radius r. We place coordinate axes such that the axis of symmetry of the rod lies along the x-axis. Okay, so so this is the x-axis, and then here we have a 60 degree. Okay, so this is a circular arc. Okay, 就是一个圆弧啦。Okay, and the origin is at the center of the curvature P of the rod in terms of Q, and small r. What is small r is the radius of this arc. What is the electric field E to the rod at point P? Okay, so here we do something similar. We try to separate this arc into many small charge element dq, and the length of this small element will be ds. Okay, so here we also assume that the charge density will be the linear charge density will be lambda. So it is the linear charge density. Okay. Okay, so here, as much as this is x-axis, and then okay, for every ds we can also find the symmetrical part. Okay, so for example, this is ds, we can always find the symmetrical element ds prime. Okay, here. So for this one will be here, this one will be here, that one will be there. Okay, something like that. Okay, we can always find the symmetrical part, and of course the charge is -2 is a negative charge, so which means that, for example, ds will generate an E field at point P pointing to the top right. And similarly, this ds prime will generate the de prime pointing to the bottom right. Okay, so this is de, this is the symmetrical part de prime. Okay, so if we do the decomposition to the x and y axis component, so here we can see that dex, the x-axis component, will add, and the y-axis component, or this one, correspond to this one. This one corresponds to this one, which is the other y-axis component, which means that this one and this one will be the same in magnitude but opposite in direction. So these two cancel each other. So finally, we only need to calculate dex, and also we have this angle to be theta, counting from the x-axis to this one. And of course, the dex will be something like, first of all, we can write it as a de equals k times dq. We also express this as lambda times ds. Okay, so this is actually dq. This is actually dq. And then over the radius. The radius is also called r squared. It's also called r. So we have r squared here. This is de. And actually, we would like to calculate dex because the y-axis component cancels. So actually, dex will be de times cosine of theta. Cosine of theta. And cosine of theta. Yeah. So here we will try to change the variable of ds. Change the variable of ds, which means that ds is actually r times d theta. Okay, using the polar coordinate. Okay, 基坐标了 polar coordinate 基坐标 okay, so actually the polar coordinate is like, we have the r-axis, we also have, for example, this point is r theta, or r theta, so this is theta, this is r. Okay, so if this is a circle, this is a small arc. Okay, suppose this one is d theta. Suppose this one is d theta. So the length of this arc will be r times d theta, which is actually ds. ds will be r times d theta using the polar coordinate. Okay, so here we have a ds over ds equals r times d theta. Okay, so here we try to plug in this one to here. So we will have de is actually k times lambda r d theta over r squared, and then times cosine of theta. Okay, so in such a way we can cancel this r with this r square, so it remains an r in the denominator, which means it becomes k lambda r, and then we write cosine of theta in the front and then d theta at the back. Because finally we do the integration over theta, and so this term is related to theta. Okay, so here we already have this dex. Okay, so here we can do the integration. E equals the integration of dex over this rod from negative 60 degree to 60 degree. Okay. So here we try to put this one to here. So in such a way we have a k lambda over r cosine of theta d theta. And it will start from negative 60 degree, but in radian will be negative pi over 3 to pi over 3. Okay, refer to negative 60 degree to positive 60 degree. So doing this integration is not that difficult. This is a constant to the variable theta. So actually we can just put this thing out. And we have integration of cosine of theta d theta from negative pi over 3 to pi over 3. Okay, so the antiderivative of cosine of theta is sine of theta. Okay, so we try to evaluate it from negative pi over 3 to pi over 3. Okay, so sine of pi over 3, sine of 60 degree is square root of 3 over 2. Okay, so this term will become square root of 3 over 2 times 2. Okay, so which is square root of 3. So finally it becomes square root of 3k lambda over r. And finally, we would like to eliminate this lambda because lambda is not a known variable here. So we would like to change it back to q. Okay, so here we would like to have the expression of q, I mean the lambda in terms of q and small r. So yeah, so we will have q equals lambda times the arc length here. The arc length here will be like, we have a 2 pi r for the, so 2 pi small r. 2 pi r, 2 pi small r for the whole circle. But here we only have 1/3 of the whole ring because it is 120 degrees, so it is 1/3 to the 360 degree. Okay, so we need to divide it by 3. Okay, which means that lambda should be 3q over 2 pi small r. Okay, so here we can put in this thing back to here. So E will be square root of 3k over small r times 3q over 2 pi r. So finally it becomes something like a 0.83 capital Q over, I mean we should still have the K, okay, so KQ over R square, okay. So actually we just merge this square root of 3 and 2 pi together as this 0.83. Okay, so the remaining thing becomes KQ over R square. Okay, so this is the final answer to this question. Okay, so any questions? 有没有问题？Polar coordinate 就是极坐标嘛？高中数学有学过吗？没有。OK， 好吧。那你不理解 ？OK， 就是圆弧的 OK， 那你就不要理会那个极坐标嘛，其实就是说一个圆的圆弧的长度啦，这个只用到圆弧的长度。那你可以理解成就是说我有一个圆的周长 它是比如说半径是 r， 那它的周长就是2派 r 嘛，对不对？那如果我只有一段圆弧的话，一段圆弧，比如说这个角度是 theta， 这个 theta 是 radian 的，它不是度数啦。它如果是 radian 的话，那这个圆弧的长度会是 r 乘以 theta 啊，会是 r 乘以 theta。因为如果你整个圆的话，那这个角度 theta 就是2派嘛，2派就是360度嘛，那就是2派 r 了。所以如果你是一段不是整个圆的圆弧的话，它是 theta， 那是 r 乘以 theta。那这边也是类似了，这边的话就是这边这个坐标的话就是意思是说，我们现在有个坐标这样，那这个是一个圆的一部分嘛，这个是一个圆弧嘛，那所以它这边是一个 ds， 那你 ds 的头跟尾啊，跟那个圆点连起来的话，那它就会夹一个角，它是 d theta， 它是 d theta， 所以这个 ds 用这个公式的话，你就会知道说它是 r 乘以 d theta， 就是这个 ds， 就是这样。还有其他问题吗？没有的话，继续吧。Okay, so here we have a checkpoint so that you can be more familiar with how we can do the cancellation. Okay, so here it says the figure here shows 3 non-conductive rods. Yeah, so one circular and 2 straight. Okay, 就是一个是圆弧啊，两个是直的。Okay, each has a uniform charge and magnitude Q. Okay, so this is negative Q, this is positive Q, so on and so forth. And yeah, Q along its top half. Okay, another yeah. 反正就是黑的就是正的嘛，正 Q 啊，白的就是负 Q 嘛。Okay, for each rod, what is the direction of the net electric field at point P? Okay, 所以就是说他问你方向嘛，你不用算。OK， 所以就是 point P， OK， point P， OK， so for the question A， OK， what is the direction of the E field at point P? Okay, so here we can consider, okay, for this part, this is a negative charge, so it will generate an E field at point P pointing to this side. Okay, so this is E, let's say E minus, okay, E minus pointing to this side. Okay, it must be 45 degree, it must be 45 degree to the y-axis and x-axis. Okay, yeah, and actually we don't need to know what is the magnitude, yeah. So we only need to know it has a 45 degree with the two axes. And similarly for this one, this is a positive charge, so it will generate E field pointing to that side, E plus pointing to the top right, also with a 45 degree with the x-axis and y-axis. So finally we can see that the x-axis component cancels. So finally y-axis component adds. Okay, so here we will consider the E field at point P will point to the positive y-axis. Or pointing upward, okay, pointing upward. Okay, and then next, this part, okay, so we separate this into 2. Okay, for the upper part, yeah, it will generate an E field at point P pointing to that side. Yeah, this is the E. Yeah, let's say this is the upper one, this is the lower one, so EU will be pointing to bottom right. Okay, I don't actually know the angle, yeah, because really depends on how far it is, but yeah, at least you need to know this EU is pointing to the bottom right, and similar, this lower part, okay, we generate E field point P pointing to the top right, okay, so EL. Okay, so you can see that the y-axis component cancel, so this will be pointing to the positive x-axis, or simply pointing to the right side. Okay, and then finally for the third case, yeah, similarly, this part will generate E field pointing to that side, and for the lower part, this is a negative charge, so the E field here will pointing to the bottom left. Okay, so in this case, x-axis component cancels, and it will actually pointing to the negative y-axis, or pointing downward. Okay, so this is a quick checkpoint to let you familiar with how to do the component cancellation, because it is an important step to do that. It will simplify some of the calculation, because if you really need to calculate the let's say for this one, if you need to calculate the y-axis component, of course you know using the symmetrical, then you should know dey will be 0 at the end. But if you need to do it rigorously using the integration, it may not be possible using hand calculation. So yeah, so it is a very important step to cancel some of the component. Otherwise, the calculation might be difficult, or maybe not possible to work with. Okay, so let's have a